Welcome to the DP Flow webinar that's on demand, partnered with Armstrong, VERIS, and Yokogawa Corporation of America. Our presenters today will be Eric Reed from Armstrong, VERIS, Western Regional Sales Manager, Lee Hamlet from Yokogawa, Pressure Product Manager, and Liz Majestic, Yokogawa DP Flow Product Manager. Today, this will be our agenda for the webinar. We'll be going over some flow meter consideration, a brief overview of the Armstrong, VERIS, Yokogawa portfolio, Yokogawa DPHarp Technology, an overview of the DP Flow principles, an overview of the Verabar Accelabar technology, and then an ideal solution for the proven advantages with combined technology, application, some specials, and if you have any questions, please email us at support@us.yokogawa.com. Now let's jump into some flow meter considerations to keep in mind when asking your customer about their application. We will start off with, what is your application? This question is important because it helps you start to think about what flow technology would be the best fit. Next would be, what type of accuracy are you looking to give? 0.5%, 1%, 3%. Pressure, temperature, velocity, and viscosity are important to know as well, and making picking out a flow meter a little easier. But there will be cases that the customer doesn't know them, and that's completely fine. Another high one on the list to ask your customer is straight pipe requirements. Do they have limited spaces or miles of piping? Are there valves before the meter? Any upstream disturbances? These considerations will affect what flow meter technology you go with. Next would be materials of construction, what type of maintenance, what output, also great considerations when deciding what flow meter you're going to go with, especially the technology. Now let's go over just an overview of what you're going to see in the later portion of this webinar. So here you have a DPHarp transmitter with a Verabar primary element with the optional RTD attached to make it a complete solution. You also have a manifold there as an added option as well. Next is the DPHarp with Accelabar with optional RTD and manifold as well. Now I'll pass it to Lee to talk about what a DP flow meter is and the DPHarp technology. Lee?
Thank you, Liz. My name is Lee Hamlet. I'm the product manager in North America for differential pressure and pressure transmitters. Liz has asked me to go over a few things. Some of them you've already heard, some terms that were mentioned. First, what is a DP flow meter? A DP flow meter basically consists of two things. It's got what's referred to as a secondary element and a primary element. The primary element is actually in the process, and it generates a differential pressure, which the transmitter, the secondary element, is measuring. Now, whether you're doing mass flow or volume flow, it depends on which type of transmitter you use, but that'll be in the next section. So cut all that out and then go on to the next slide. So primarily what I'm going to talk about is the secondary element, and there's two different secondary elements that Yokogawa offers. One is just our straight differential pressure transmitter, and the other one is our multivariable transmitter. Both use the same DPHarp technology that Yokogawa's become famous for. That DPHarp technology is a very futuristic, very modern way of measuring pressure. Basically, our sensor consists of two resonators that are located on our circuit board. And when the pressure is applied to it, the two resonators, one goes into compression and one goes into tension. Basically, it means when the pressure is added that the frequency that the two oscillators are resonating at change. And by knowing that information, we can develop what the actual pressure is. So you see on this chart, we've got a green and red line representing the two oscillators. they're resonating, they could apply pressure to them. One increases in frequency, one decreases in frequency, and based on the difference of the two frequencies, we know what the pressure is. So this has some advantages. It's a digital sensor. It's got a large turn down, very accurate, very repeatable. It's got a very long term stability, depending on which model you get. Our EJA series has a 10-year stability. Our EJX series has a 15-year stability statement. One of the big advantages is that it's multi-sensing. Our sensor can tell you not only the differential pressure, but can tell you the static pressure on either the high or the low side, and it can also give you approximation of the temperature. There is also an added advantage since we have two separate oscillators that we're able to meet a SIL2 certification in single use. All of our transmitters are standard that way, which means they are very safe devices. So now I'll hand it back over to Liz.
And the next portion will be Eric Reed from Armstrong VERIS.
Okay, as Liz mentioned, my name is Eric Reed. I am the Western Regional Sales Manager for Armstrong International, specifically the VERIS Flow Measurement Group. So we have a very full product portfolio of differential pressure and vortex meters. Today we're going to be talking about the Verabar, or the averaging pitot tube, as well as the Accelabar technologies. To start off, we're going to go over the basics and how DP flow works. As Lee mentioned, essentially a DP device, or the primary device, is putting an obstruction in the piping in the process itself. And so there's two laws that really kind of define how differential pressure works. One is the conservation of energy. Essentially it says whatever goes into my pipe has to come out. We're assuming there's no losses due to friction. And then when we put that restriction, whether it be any type of DP device, the averaging pitot tube, an orifice plate, venturi, whatever that device may be, essentially we're reducing or putting an obstruction in the piping. So in this case, you can see that there's a decrease in the line size of the pipe itself. Because we still have the conservation of energy, which says whatever goes through has to come, whatever comes into the pipe has to come out, something has to change within the process. So in this case, the velocity increases and the pressure decreases after that obstruction. And that differential pressure, or the change in the pressure from the upstream to the downstream side, is the differential pressure that Lee talked about with the secondary element that's measuring that. And that differential pressure is proportional to the flow, which is what all of the differential pressure is based upon. I want to talk a little bit about the basic equation for mass flow. I don't want to get too much into the meat of this, but essentially just kind of go over some of the important concepts or the different components of the equation. So we'll start out on the left side. The FNA is our units conversion factor. So it depends on what units we're trying to output, whether it be for steam, we're looking for pounds per hour, a gas where we're doing standard cubic feet per minute. That units conversion factor will change to output the units correctly. The K factor is an experimentally discharged coefficient factor that it basically equates it back to a true flow. The D in the equation is the pipe diameter, and you can see that that term is squared, so that becomes quite important that we know the ID of the pipe. Y sub A is our gas expansion factor. This becomes very important for gas flows if your differential pressure over your pressure ratio changes, that gas expansion factor has a larger impact on our mass flow equation. Under the square root, we've got two terms. One is the differential pressure that we're measuring. The other is the density. So if we're measuring a incompressible fluid such as a steam or a gas, this becomes very important as our temperature or pressure changes. So just for easy numbers, if our temperature and pressure changed enough to where our density was varied by about 4%, if we're not taking into account that density equation, we're going to be putting about a 2% error into our mass flow uncertainty. And this is where so the mass flow is usually where we're using the multivariable transmitters that allows us to take into account the changes in density. If we're measuring, say, an incompressible fluid, such as the water, then we typically don't take that into account, and we can use a differential pressure transmitter. Okay, we're going to start off talking about the Verabar technology. So this is, if you look at the picture on the left side, you've got the Verabar that's installed in the pipe. You can see that the sensor, this is a insertion type device, which basically means we're inserting it into the pipe. It's not, there's no need to cut the pipe out and put a flange section in. Basically, we're drilling a hole in the pipe and inserting it in there. Looking at the picture on the left, we've got the flow coming from the left side. It impacts that high side of the sensor, creating that high pressure, creates a vortices as it gets shed, and we've got our low pressure. So if we go over to the right-hand side and look at the picture, here's a little more detailed kind of illustration of the shape itself. You'll see that the flow's coming in. We've got our holes on the front side, which is where we measure the high pressure or the impacts side of things. And then we're creating the vortices that's with the holes on the downstream side, which creates our differential pressure. A couple things to note about the vortices. With the averaging pitot tube and all of the differential pressure products, we're creating that differential pressure by the velocity that comes across there. So with the Verabar, we like to have the Reynolds number above 20,000. Now the Reynolds number is a dimensionless number that equates regardless of the fluid, what the velocity is. So when we're measuring steams and gases, we're going to be seeing higher velocity or higher Reynolds numbers, upwards of 20,000 to 1 million. When you start to get into some of the more viscous materials, something like a molasses or a gear lube, some of those we're going to have to make sure that we're creating that Reynolds number over 20,000 because we have to shed the vortices in order to create that differential pressure. So some of the differentiators for the shape, essentially you look at the shape, it's a wing design, so we've got very good structural capabilities with that because of just the way that it's manufactured. Essentially it starts out as a three-piece design that gets a full penetration weld down the sides, and then it gets machined down back, so we have a very consistent shape from lot to lot, or so if you order a probe 1 week versus in another year, they're going to be very consistent from shape to shape. 316 stainless steel is our standard material that we use. We can do exotic materials if the application requires it. Some of the advantages of this is the fact that we've got a roughened surface on the front, and this helps us to predict where that vortice gets shed. So as we cover the range from 20,000 to, say, 1 million, we want to be very consistent on where that vortices get shed because as we start to shed that, we've got the holes on the side, which creates a nice quiet signal, but it also helps us as far as any entrained debris. So, we like clean liquids, gases, and steams. We know in the real world those don't always happen. There's scaling on the pipe. There's some sort of debris in there. So this allows us to reduce the impact of any plugging. One of the things you'll hear about, or the complaints about an averaging pitot tube, is that the holes get plugged. And this, by having the holes on the side and allowing the vortices to shed and take the debris towards the back, we reduce that impact significantly. Next, we'll talk about installation and orientation. So this becomes very important when you start to look at the different applications on how we install these. And really it becomes very important when you're generating a lower differential pressure that we're trying to measure with with the transmitter. So if let's start on the left side, we're going to look at the liquid or steam mount. We like to be at the 6 o'clock position plus or minus 80 degrees. Best practices, we prefer to be at either the 5 o'clock or the 7 o'clock position. This allows, if there's any entrained debris in there, it allows free flow on the bottom side of that pipe. And the reason we like to be on the bottom side of the pipe for liquids and steams is any entrained air, it allows us to bleed that out. So, one of the nice things about the Yokogawa DP or multivariable product lines is that with the DPHarp sensor technology, it becomes very positionally sensitive. So we like to get these in there, get them zeroed so that we've got a nice zero, clean zero, and then they're very stable. When we look over the next one, the gas, we like to be at the 12 o'clock position plus or minus 80. And once again, best practices, we would prefer to be at the 1 o'clock or the 11 o'clock position to allow any debris to free flow through the bottom of the pipe. For gas, because we're on the top now, if we've got any entrained liquid, it allows, by gravity, we can bleed that out and maintain that good, crisp sensing element. If we go on to the next side, we've got our vertical pipe. So once again, we can rotate anywhere around the pipe and mount it anywhere. But if you'll notice that the orientation of the head is such that we rotate that 90 degrees from a horizontal line, and that allows us to not have any height difference from our high and our low pressure, which, you know, would artificially add some differential pressure. So it's very important that we know whether it's in a horizontal or a vertical pipe. Once again, for this, we like to have gas flowing up, liquid or steam flowing down. So now we'll talk about some of the advantages of the Verabar flow measurement sensor. First and foremost, I want to talk about the ease of installation. The installation of these meters is quite simple. You can look on the picture on the right. Essentially, you drill a hole in the pipe. In this case, we've got a threaded model, so you've got your threadlet, roughly about 8 inches worth of linear welding, so very simple and easy to add that to as a measurement point. Because of the testing that we've done, we've got an improved accuracy and turn down. As I mentioned, the sensing holes on the side allows us to reduce the clogging or the impact of debris in your flowing medium. Also, the holes on the side gives you a very nice, clean, stable signal. Once again, we do like the Reynolds numbers to be above a 20,000. Flow turn down, we can get up to 10 to 1. This is all application dependent, so we size each and every meter that comes through the factory. We like to make sure that it meets the customer requirements and that every application is slightly different, so we like to look at each and every one of these. Some of the different models that we have to talk about on this is, you know, when you start to look at the different codes, the picture on the left shows a threaded model. This is for a lower pressure application. We also have a flanged application for, which basically has a weldolet with a flanged mounting hardware on there. That's for higher pressure applications. And we also have a flow tap device. The flow tap device allows us to insert and retract under flowing conditions. And we've got some pictures, and we'll talk more about how that becomes advantageous for different applications. Because of the wing shape, we've got a very good structural calculation, and that's another thing that we'll do when we do the sizing is we look at what the flow rates are, how it matches up with the model. Is it structurally sound? You know, if we've got a very high velocity, there's things that we can do with the model codes and or sensor sizes. We've got 3 different sensing element sizes that we can make some slight changes to really optimize that application. There is a 5-year performance warranty on these. One of the nice advantages of the Verabar technology is there is no moving parts. The geometry is fixed, so we get a very consistent, repeatable measurement. Our standard product offering is 600-pound ANSI and below. One of the nice things or the advantages of the VERIS flow measurement group is we're a little smaller company, so we're quite nimble and can handle the specials. So we realize that not every application falls under the categories or the catalog selections. So if you have an application that's a little more difficult, you know, talk to Liz and the guys, and they'll speak to the VERIS factory guys, and we can kind of go through and we can design a special application for you. The line sizes for this is the smallest we can do is 1.5 inch. We've done up to 22 foot for a stack measurement, but there is no limitations on square, round. So we have lots of different applications as far as mounting hardware. So the next one we're going to talk about is the Accelabar technology. Let me step back one more thing. Let's talk about straight run a little bit with the meters as part of the selection criteria. With the Verabar, we're looking for anywhere from 7 diameters upstream to 24 diameters. So 7 diameters is after a simple elbow, maybe a concentric expander reducer, and 24 diameters if you have like a butterfly valve. That butterfly valve induces swirl, and so we require a little bit more straight run. We also would like to have 3 diameters downstream. So there are different mounting configurations and options associated with the Verabar. The next one we're going to talk about is the Accelabar. So this, once again, uses the Verabar technology for the actual measurement itself, but now we've got an Accelabar body. So this Accelabar body has some nice advantages for us. It requires no straight run up or down and increases our turn down. Those are the 2 big benefits of that. Let me go into some of how the Accelabar body works. So essentially we've got the flow coming in on the left side. We've got a toroidal inlet, kind of a dual inlet geometry that conditions the flow. And you'll notice that where the Verabar is installed in that is the line size has been reduced. As what that does for us is increases the velocity and helps us to increase our turn down. So the turn down we mentioned with the averaging pitot tube was roughly 10 to 1 based on the application with this. With the Accelabar, we've gotten up to 65 to 1. Typically is what we see based on the application is anywhere from 20 to a 35 to 1 turn down. You'll notice that each one of these has a thermal well that you can mount an RTD in there. The thermal well is a fully welded thermal well, so there is no leak path. And then we've got our diffuser section on the back side of that, which helps to reduce the permanent pressure loss that we see on these. Once again, for the orientation of this, so for liquids and gases, we look at the right side, or for liquids and steams, we look at the right side where we're at the 6 o'clock position plus or minus 80. Once again, best practices, we'd prefer to be at the 5 o'clock or the 7 o'clock position. And for gas applications, we're going to be at the 12 o'clock position plus or minus 80 degrees with the best practices of 1 and 11 o'clock. Another thing I didn't mention is the fugitive emission. So when we have different configurations for each of these devices, whether it be the Verabar or the Accelabar, and it's what we're showing as the direct mount option. The direct mount option versus compared to a remote mount option, we have about a 25% reduction in leak path or fugitive emission points. So depending on the application, that becomes quite an attractive option because we have less leak paths. It is somewhat dependent upon the pressures and temperatures of the application. So it's something that, as I mentioned, we size each and every one of these. So we'll look at the application. If you have a very, very high temperature application, then we'll typically go with a remote mount so that we keep the temperature at the transmitters below the sensor levels or the limits. So some of the advantages of the Accelabar. So once again, the big thing is there's no straight run required. Question gets asked quite a bit. Well, there's no straight run. Do you have test data? We have quite a bit of test data on this. There's a flow test data book that will be coming out to highlight some of these. Each of these were tested at independent flow labs such as CZ in Nunn, Colorado, Southwest Research in Texas, and Alden Labs for water. So we have a lot of testing on these. There is a footprint required depending on the line size. So these go anywhere from 1 inch to 12 inch. And the length of these goes anywhere from about roughly 8 inches to 30 inches. So there is some footprint, but there is no straight run required. So you can mount directly, as the pictures show, after an or a reducer, valves, or an elbows. The accuracy of these is 0.5% over the entire flow range. But the big thing about the differential pressure, once again, is the repeatability. And Liz talked about the repeatability being one of the big factors. And because we have no moving parts, it's a very simple device. We have very good repeatability. There is no calibration required in the field for these as well because of the consistent geometry. As I mentioned, with that reduction of the line size in the Accelabar body, we get a higher turn down. Once again, we size each and every one of these, and this is application dependent, but we see anywhere from 20 to 35 to 1 on a typical basis. So once again, we're creating a very good, strong differential pressure signal with that reduction in pipe size. And when you marry that with either the differential pressure, the EJ, the 110 or the 130 series, or the multivariable transmitters, the 910 or the 930 series, you get a very good, repeatable, strong measurement. Next thing we're going to talk about is some applications. So start off with the industrial side. There's really no limitations on the market. We've got a lot of applications in the oil and gas, chemical, food, pharma. When we start to talk about the food and pharma as well as the paper, we're usually looking at the utility side just because of the design or the shape of the probe that's measuring this. We don't meet that clean, the clean requirements for the food or pharma. Some of the applications, the DPFlow technology is the most commonly used or the highest use of flow meters in the world right now. And the reason for that is it's a very simple device. They're tried and true. They've been around for a long time. Very easy to diagnose if we're having any issues in the field. Some of the applications we see for these are chilled water systems. We've got a lot on cooling water applications, combustion air, process steam. One of the things we see a lot of is on the distribution steam side of things, and where the advantage of the Accelabar is that higher turn down. So if a customer has a large turn down, we're able to measure that full range with one device. It becomes very consistent, a nice feature, and able to calculate the efficiency or actually for billing different as you're distributing steam through different areas. Landfill gas is another one that's we're starting to see a lot more applications with on that. So some of the natural gas applications, natural gas to boilers. So when you start talking about the boiler applications, we've had applications where we've got 4 Accelabars on a boiler. One is for the feed water. One is for the primary gas that's being fed, which is typically a natural gas. There's usually a backup, which is a propane, so we use an Accelabar on that, as well as the outlet of the steam, and measuring the steam on that. We've got natural gas blending stations. Coal bed methane is another where we've had a lot of success. And this is a little more of a difficult application where there's the coal fines. And as we mentioned, the shape is what really helps us with that, with having the holes on the side. You get that velocity up there. You've got those coal fines, and we have no issues with the plugging on the holes. Anytime you're looking at skid mounts or little skid applications, the Accelabar becomes very attractive for this because of no straight run, reduces the amount of straight run that's required, so the footprint gets reduced significantly. When we start to look at the Verabar applications, as you start to get to larger line sizes, say 8 and above, it becomes quite cost effective. Now, we'll size each and every one of these to make sure that we're generating enough differential pressure, but those are some of the advantages in some of the applications that we have. So from the institutional side of things, we're covering the higher education, healthcare, government, district. Once again, we've got a lot of the same applications. Anywhere you walk around and look where you want to add a measurement point, for the most part, we can find an application where we're going to work with the Accelabar or Verabar. Once again, the district steam, the boiler systems where we can put those on any component. But the big thing is for submetering. When you're doing steam applications is where we've had a lot of success measuring different, from the campus side of things where you're measuring into different facilities. It allows us to put that in, and the no straight run is also a big item. You go into a lot of the higher education, they're older buildings. You go into the steam room, there's really not a lot of straight run. This allows us to add a measurement point pretty much anywhere within the building without changing piping configurations. So it becomes quite cost effective from that standpoint. A couple of the examples of this. So if we start off, we'll look at the left side of this. This is one of our flow tap devices I mentioned. This is the one that can be inserted and retracted under flowing conditions. This one is a vertical application, so you can see that the head is rotated at 90 degrees. We've got a higher temperature app, so we've got a remote mount configuration. So this allows us to keep the sensor limits or the temperature at the transmitter below the sensor requirements. If we look at the picture on the right-hand side, we've got an Accelabar mounted in a very difficult application. So we've got it sandwiched in between a couple of valves, and because we condition the flow prior to the measurement, we're able to measure this accurately and repeatably. Next thing we'll talk about is specials. Now, from the special side of things, we've got a lot of illustrations showing different mounting configurations, but that's really not the limits of the specials. We've got exotic materials that we have utilized in the past with, not 316 stainless is our standard. We can do Hastelloys, the Monels, the super duplexes. So if your application is such that it requires an exotic material or a different configuration, higher pressure limits, we have the ability to go through and engineer those to order. And here's just another example of a special with the Accelabar. Once again, higher pressures, 316 is our standard, and it's actually a cast body, so it's a CF8M. But if you've got something that's a little more challenging of an application, we'll go through and analyze that, design the best application, whether it be a change of material, higher pressure limits. We have the ability to do that. So when you start to get into some of those applications, talk to the Yokogawa factory. Let's figure out there's 5 items that we like to have to size these. We like to know what's flowing through your pipe size, your pressure, your temperature, and your flow rates. We'd like to know the maximum and the minimum flow rates so that we can make sure that we could cover the entire flow range.
Thank you again, Eric, for going over the Accelabar and the Verabar technology and the basic principles of DP flow and some of your specials and applications. Wonderful. That was a good overview. The next one thing before the quick overview we didn't discuss is software. There is software available called VeriCalc. It's a sizing tool for both Verabar and Accelabar, and it's user-friendly. But if you're a bit wary of sizing your own meter, please contact Yokogawa to assist. You will find the VeriCalculation on the Armstrong VERIS website. They do recommend, they do have where you have to fill out a registration, and it'll get sent to them, and then they will send you an email with how to download the sizing tool. So if you have any questions at all, just email both either Yokogawa or Armstrong VERIS about the sizing tool VeriCalculation. So to conclude with the ideal setup, we learned the basics of the DP flow measurement, a few flow meter considerations to keep in mind when you're sizing out, either using a Verabar or Accelabar, and in a certain application. Also, we learned the Yokogawa transmitter DPHarp unique sensor and the Armstrong VERIS Verabar and Accelabar unique flow design. And by combining these two technologies together, it makes the ideal setup and package solutions for DP flow applications. So there we have it. We have the complete overview for the DP flow webinar. This is on demand. You can re-listen to this at any time. For the VeriCalculation sizing tool, please go into the Armstrong VERIS website and you will be able to register for it to get the sizing tool. Thank you and have a wonderful day.